Please have your computers ready, okay?
Are we doing Excel? Are we doing Excel?
No, no Excel. So it's gonna use the game. No game. DOS. No DOS, sorry, not DOS, I mean Windows.
Okay.
Windows program that my wife wrote. Okay.
Please have your PCs loaded. We're going to be running a Windows program. If you haven't downloaded yet, you should have downloaded 3 files from in the same directory. 3 files from the class website. Start 2 minutes of break. So, those 3 files, MSFL, Excel, GRD, the 2 MS files, and the AAS, ECH 4323, and B, should be in the same directory, should be in the same folder for it to run. If you don't have the 3 in the same folder, the class program will not run. So make sure the very first thing is to go to the class website, download those 3 programs. Let me actually go to the class website and show you.
Yeah, it's not a good sign.
Interesting. It has as a background of seeing what it should be seeing. Oh. So the 2.ocx files and the AAS 4323 NP. Those 3 files should be in the same directory, otherwise the program will not run. So where I have this is the main program, and you have the 2.ocx files.
Do they have to be next to the DOS box? The DOS box?
No,
Oh, okay.
you just have to have them in the same file. That's all. All right, our break is over, guys. I read through what we had here before we go to the software. frequency 1 over tau, and since it's log scale, the corner will appear in the plot at log of 1 over tau. The phase line has two parts. The minus tan inverse of omega tau. That's this purple line. It starts at 0, ends at minus 90, and it's minus 45 at the corner. The minus omega d is an exponential decay. It's this one. I drew it here what would be the case if the delay is small. If the delay is small, what you will have is, at the beginning, since the delay continuity stays pretty much to 0, it's going to mimic the minus tan inverse. But once the delay starts taking off, that gets added and you add a negative number, so it goes below that. So this point here is the sum of this value plus this value. Remember, 0 is here. This is 0. Okay, 0 is here. Okay? So, at this point, I'm adding this value plus this value. The sum of those two values is this value. Once this is minus 90, the sum is the delay, the minus omega d minus 90. This is 90 degrees below moving thing. Clear? So, let's go now to the class software and see this. And I'll do a couple of examples, some with small delay, some with larger delay, and you'll see it's clear. So, you need to have downloaded in one folder the 2.ocx and the AAS and P. Hmm?
It won't let me download the OCX file because it says it's corrupt.
It's not corrupt. Everybody else has downloaded it. I just downloaded it now. It's definitely not corrupt on the folder.
I don't know why it's not letting me.
Run it? But don't try to run anything.
I'm just trying to download it.
Yeah.
Which one is it?
Somebody put it in a USB and give it to her. Do you have an extra USB, Doc? I would give her mine, but everything's running off of mine.
Like I figured it out.
Okay.
Okay? Don't try to run the OCX files. They won't run. They don't execute them. Then, if you, to be on the safe side, right click and run as administrator. Let's see, where is it run? Run as administrator. Okay?
Oh, mine said it was
Most, you don't need it for likelihood, but I'm avoiding some problems by telling you to do it that way first. So once in many hands, that's all right.
What's the AAS?
Right. Yes. Yeah. And you should see this screen. You see this screen, we are okay. So I'll do a couple of examples. Well, maybe 2 or 3. Let's do one. So
1 second. Hold on.
I may regret what I'm erasing. So, example 1.
You did it?
Let's take for K 100. Let's put down 10s plus 1. And let's take the delay really small. And I'm saying small in comparison to the tau. So if I make it 0.01, so first example, let's do K100 tau 10 delay minus 0.01. I'm using powers of 10 so we can easily see numbers on the clock.
Mine won't run.
Is everybody seeing this? Who doesn't have this up? Okay, I'll give it to you some time. Remember, you need to have in the same directory the two OCX files. Otherwise, it won't run.
I have mine and it doesn't run. I'm just gonna like look at somebody's computer.
Okay, so just double click the first one.
Yeah, but as soon as I try to like run it, you can just and everything has like the same code. I'll just do it on
Let's see if right clicking.
That doesn't do it. Look at it work.
How do you right click in Macintoshes?
How do you do it?
Two fingers.
No, it's running on Windows though. Control click.
Oh, on Windows?
Yeah,
I two finger.
with 2 fingers.
Try. Who else has a problem? Are you okay now, Shannon? Okay. So, show him how to run as administrator. Mika, are you okay now? John, are we okay? So, as you can see, the program says this gives you the frequency response of an open loop transfer function of the form e to the minus ds times a polynomial a of s in the numerator divided by polynomial b of s in the denominator. The result can be plotted as a body plot or as a Nyquist plot. Now we're doing body plots. Also, the degree of b of s does not exceed 6. The poles of b of s are calculated to assist in the stability analysis. So, did it work?
No.
No? Download it again.
Yeah, I'm gonna try to download it again.
Maybe somehow it got corrupted in the download. I need to move on though so you forget it.
Yeah, that's fine.
So click to continue. So for our example, that time, that's the time delay. Yeah, that's another synonym of time delay, that time. So that's 0.01 for the example that I put up there. So put 0.01.
Wait. Oh, no, yeah. Good.
All right. Entering moves you to the next one. Degree of b, that's the denominator polynomial. So what's the degree of our denominator polynomial in this example? 1. And press enter. You need to press enter after the value you enter. Notice you enter the denominator polynomial. Notice you enter it with the lowest power first, the 0th order term first. Okay? So we're entering it 0th order term first. Okay? So what's the 0th order term of the denominator? 1. And B2 is the next term. What's that?
10.
10. Now we move to the degree of the numerator. What's the degree of the numerator?
0. Wait. When you click 1, you press enter.
Enter. You need to press enter. I mean, it tells you with the big window there.
And
Press
then
enter every
10.
time.
And then 10.
Enter. 1 enter, 10 enter. After you press 1 enter, it will give you the next one. And you can scroll to see that you got it right. If you move the arrow, you can see your B1 should be 1, your B2 should be 10. Let's click now on A1. What should be the value for A1? 100. Okay? Press enter. So that should be the enter we should have all. 0.01 1, 10, 1 to B1, 10 to B2. And here we have the two values. B1 was 1, B2 was 10, 0, 100. Click here to continue. It gives you open loop walls. And now it's a question. Do you want to see the real and imaginary parts of G of I omega for a specific frequency? We'll be using that sometimes to establish boundaries. I'll talk more about it when we have the stability analysis. But at this point, let's say no. Is everybody caught up? Did it work now, hon?
No, I'm starting down one minute.
So click no. And now here it is. The plot is from minus infinity to plus infinity. Obviously, you can never plot from minus infinity to plus infinity. So you need to pick a minimum and a maximum frequency. So we definitely want a minimum frequency less than the corner frequency. And what's the corner frequency here? What's the corner frequency? 1 over 10. 1 over tau, right? The corner frequency is 1 over tau. My tau is 10 in this example. So it will be 0.1. So I want something less than 0.1. Let's go to all orders of magnitude lower than that. So let's put 0.001. Maximum frequency. Well, I may want to come back and change it. Let's see how it will do. Question?
Was it 0.01?
Yeah, 0.001. Yes. And maximum frequency, let's put 10 might be too high, but the delay is small. Let's put 1 first. 1, maximum frequency. Now, this is something that I wish I hadn't done. When I wrote my program for the Commodore 64, this program was not running very fast. So, how many calculations you made mattered a lot. If it took 10 minutes to run, that's not good.
When did you write this program?
In 1982, original for the Commodore 64. Well, this is so much improved. The interface is totally my wife's and everything. If you like this interface, it's totally hers. Play with EX5, you'll see what I have done. You'll see how much superior this is. But anyway, so, and 1600 points was taking maybe 20 minutes to run, I don't know. So I had put a maximum number of points, 1600, and I never envisioned more than that. Anyway, 1600 is plenty. But there's no reason, now it's instantaneous, guys. So there's no reason to ever run less than 1600. So this is wasted time that you have to enter 1600, sorry for that. My fault, I didn't tell my wife to change that. So 1600, enter. It immediately generates a table of data that we can scroll through. It has, look at the columns. Okay, forget about the row number. Log omega is the first one. Since we start with 0.001, log base 10 of 0.001 is -3. Okay? And we'll end up at log 1, which is, I probably will have to change and make a bigger frequency, maybe change it to 10. But it will end up at 0, and of course, since the computer is not totally accurate, instead of 0 it gives you -2 times 10 to the -3.